All right, so we're just getting this stream started, and I'll go ahead and share the link in just a second. If I can track it down. My name's Tovio Roberts. I am not always the person who streams. It's usually Clark Walker, and I'm likely going to be streaming 1 day a week for the study hall. We're aiming for Fridays. And yeah, so my hope is that this link I'm sharing is the correct one, and I'm just going to double check that really quick to make sure. And it doesn't appear to be, so let me see if I can sort that out. This is what I get for not streaming for a really long time. Let's see if I can. Aha. I think I figured it out. All right. So if you're in the Slack and you saw and you clicked on the link, that probably took you to a video that was already recorded. I just updated the link in Slack. So as always, feel free to ask questions in Slack in the relevant Slack thread for Study Hall. It's in the Study Hall room in our org, which is DSI Prep, which I can put in our description really quick. Maybe. Sorry, I'm gonna bumble. This is my first day of doing this in a really long time, so apologies in advance for that. Or in real time for that, actually. So yeah, if you go to if you Google Galvanize DSI Prep and you click on that data science prep courses link that comes up, there is the data science basic prep, and you can go ahead and enroll in that if you're coming across this without without seeing this this post from Slack. And it looks like that is in the description. Okay, I think everything's good. So that, go ahead and let's actually do something. So if you have a question, put it in the thread. And if it's a question from Learn, we can jump over and look at that, and I'll go ahead and walk us through a solution or hint at some ideas. So pretty recently met with a student regarding list iteration, and I'm just gonna track down my notes for that really fast, because I think there are a number of students in our premium prep right now who are feeling a little bit stuck, and I think that kind of happens pretty quickly, pretty easily around around this time. So I'm just gonna and if there are any issues with my sound, if it's not loud enough or anything like that, please let me know, and I will correct that. One thing I probably should make sure of is that I'm using the correct microphone. It looks like I am. Okay, I think we're good. All right. So yeah, let's actually do something. I like to well, in the premium prep, we spend a fair amount of time focusing on concepts related to counting and sampling. And these are sort of rudimentary algorithms that we can think about. Like, how do we count? You know, how do we count in a number system? And what do I mean by a number system or a counting system? Well, let me kind of illustrate that. Let me illustrate clearly what I mean by that. Let's say we have, and you know, I know we all know this, but let's say we have the values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Actually, not 10. Scratch that. 0 through 9. These are all elements in what we would call a base 10 system, right? These are all elements in a base 10 system. So if we're going to count, one place in a base 10 system, we're going to do something like this. We're going to say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? We're going to do that. Now, if we're going to count in a base 10 system that has 2 places, right? So this is one place here. And if we're going to count in a 2-place system, we're going to think about this like 0, 0, 0, 1, 0, 2, and so on up to 0, 9. And then, so from 0, 9, we're going to flip this back over to 0. It's sort of like we've got 2 wheels, right? And it just flips back over to 0. And when that happens, it increments the next place by 1, right? And of course, we can go down to 1, 9, and then that's going to flip over to 2, 0, and ultimately we're going to get to 9, 9. And if we only have 2 places available, when this flips back over, it's going to be back to 0, 0, right? So counting can be a really powerful way of thinking towards probability. And to demonstrate that, I'm going to use kind of the thing I always use. Cat, dog, I don't know, let's do fish, right? Let's just use 3 animals. And I'm going to represent these as capital C, capital D, and capital F. So if we want to count in this system, in this cat, dog, fish system, first thing I'm going to point out is that there are 3 elements, and thus this is going to be a base 3 system, right? Base 3. So if I want to count one place in a base 3 system, this is going to be cat, dog, fish. Depending on what order we're considering this, let's think of cat as being, let's keep this in order, and we'll keep cat at the bottom, and we'll put it in first. So cat, dog, fish. That's every possibility with a base 3 system with 1 place. So let's do 2 places. We'll do cat, 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 dog, cat, fish, right? And then we're going to flip fish back over to cat. We're going to do dog, cat, dog, 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 fish. And then we're going to flip this over again, back to cat. And we're going to do fish, cat, fish, dog, and fish, fish. Okay, so that's 2 places. If we want to do 3 places, it's the same idea, right? So cat, 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 dog, cat, cat, fish, cat, dog, cat, cat, dog, dog, and so on. And at some point, we're going to get to cat, fish, fish, and we're going to flip both these over so that we get dog, cat, cat, right? And dog, cat, dog, and so on. So, there are some small things to notice here. How many possibilities are there, or how many, if we've got one place of base 3, how many values are there? Well, there's 3 values. So how many values are there in 2-place base 3? There's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there's 9 there. And then, well, let's take a guess as to how many places there are, or how many elements, how many numbers, however you want to think about that, there are in 3 places of base 3. So we've got 1, 2, 3, 4, 5, and if we think about it, if we were to write all of this out, what we would see is 27. And there's a pattern here that you might be seeing, that might be emerging, where the number of places is the exponent. So we're taking the base to the exponent, right? So this is 3 to the 3rd power in this case. 27 is 3 to the 3rd power. And we can say, okay, well, in 9 places of base 3, we would have 3 to the 9 different elements in, that are composed, right? Well, what do I mean by composed? Well, how do we compose this? Turns out this is fairly easy to compose. There's a question. What's the topic being discussed right now? I'm talking counting. More generally, we're going to use counting as one of our bases for probability. There are sort of 3 bases that we're going to use for probability, but you could argue that there's just 2 in a sort of functional way, or an applied way, and that's going to be counting and sampling. And then we also have concepts related to set theory that underpin probability. But I think it's really helpful to start with counting. And that's what we're going to do in Premium Prep for anybody in here who's in Premium Prep. We're going to spend time counting. And counting looks like a few different things for what we're talking about. This is very basic. This is sort of like the fundamental counting where we are exhaustive and we allow repeats of specific elements, right? We can have cat, cat, cat. And we haven't applied a rule on this that cat can only appear once or anything like that. So let's code this, and this is going to be very simple to code. And this is only one way to code it. There are other ways, but we're not going to get into recursion in here. So I'm just going to do this with nested loops, this form of counting. So first I'm going to make a list with our elements in it, our different numbers, our cat number, our dog number, and our fish number. And this is going to be, let's just write this out. So for animal in animals, we're going to get that's going to get us cat on the first round of that loop, then dog, then fish, right? And let's call this animal 1, just to do that. And then we're going to make an animal 2 and an animal 3. And if we print this, if we print the result of this, and I'm going to put these in a list, animal 1, animal 2, and animal 3, and we run this, we're going to see all the different possible ways that we can have cats and dogs and fishes. You might want to imagine a scenario where we have let's not say a bag. We have a place where we can select a cat, a dog, or a fish, and we can select that animal, look at it, put it back, close our eyes, select another animal, look at it, put it back, and do that 3 times in a row. These are all the possible ways that can result, right? We can get cat 3 times in a row. That's totally fine. We can get dog, then fish, then dog. We can get 3 fishes, and so on. So this is counting, right? And there are things there are things, places we can take this, a number of places we can take this. I'm not going to get so much into that here, but you know, you can take this into permutations, you can take this into combinations, and that's fairly straightforward. But what I want to do right here is answer some simple questions. And let's do that as, well, let's do that in this procedural way using Python. Oh, I need to do .append. Okay. Let's ask questions. So choosing, you know, these three animals with replacement, what is the probability of choosing at least one cat? How do we go about starting to answer that question? It's fairly easy. We can just iterate over counting and select all the lists that have one or more cats. And how do we do that? Well, let's do one. We'll make a variable. We'll call it one or more cats. And that'll be a list. And I'm going to say for animal arrangement in counting, we can just say if the animal arrangement dot count of cat is greater than or equal to 1, then we can collect that list into one or more cats. And we can append the animal arrangement. So we can take a look at that, you know, for arrangement in animal, in one or more cats. We can print those arrangements and take a look at what those look like. And I don't think we should be too surprised by this. Every one of these has a cat in it, at least one cat. We started cat, 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 and we go down to fish, fish, cat. Okay, so we haven't answered this question, what is the probability of choosing at least one cat, right? We haven't answered that. But now that we have this one or more cats, we can do something fairly simple. So let's just visualize this as, here's the pool of all these different arrangements of these animals, arrangements with replacement. There's a subset of this pool that looks like one or more cats. And so we can think about probability as being sort of the area, or, you know, how many items are in this subset divided by how many items are in, or how many arrangements are possible. So how many arrangements are in the subset divided by how many arrangements are possible. So let's just do that. That's very straightforward, very easy in Python. We can say this is the length of one or more cats. And I should just do this. I keep making typos. Divided by how many are in counting, in this case. So if we print this and take a look at that result, it looks like 0.703 or 0.704 probability. And, you know, we might ask ourselves, you know, does that make sense? Well, it makes sense if we just think about this as, you know, you're blindly reaching into this space. You know, if we only had cat, dog, and fish, you know, if we're only selecting one, what would be the probability of getting a cat? It would be 1/3. What's the probability of getting one or more cats if we're, you know, selecting 3 animals? This makes sense because we take that subset of arrangements and we divide the amount of items in that subset by how many items there are total. And that's a very simple way of thinking about probability, and it's simple, but it's also very powerful. Are there other ways to answer that question? Yeah. Here, let me paste this in. If you're following along, let me paste this code snippet in to the Slack, just so that you have it there. So, yeah, essentially, we can start answering these kinds of questions. So let's think of another question. What is the probability of choosing 3 fish? That's another question that we can try to answer. Choosing these 3 animals with replacement, what is the probability of choosing, 3 fish? Well, there's only one way to choose 3 fish. However, we can still take this same approach, the same kind of filter approach, and I'm just going to adapt this, so let's call this 3 fish. 3 fish. And for each animal arrangement in counting, if the animal arrangement.count of fish is 3. Not 1, but 3. Then we can just print out the length of 3 fish divided by the length of counting. And it looks like that's 0.037. Well, what is 1 divided by 27? That's also 0.037, just to verify that this is doing what we think it's doing. Okay. We can ask more complex questions than this. And notice that in the asking of these questions, what we're really doing is kind of filtering through and having some kind of logical question. We're putting in some kind of logic question here. We're counting the cats, and we're going to get a true or a false from this for every item, for every element in in counting, every arrangement of animals in counting. And if this evaluates to true, then we're going to throw that into this filtered set, this subset of this containing set that we're seeing. And there's a nice simplicity to that, I think. And also, the main lift here, the main thing that you have to figure out using this kind of strategy is how to construct the conditional statement that we're seeing here. That's really what this is coming down to, if you think about it. This pattern is easy. We could replace this with a list with 10 items instead, and this would be the same, the same type of problem, and we would have different probabilities as a result. We could swap out, what these elements are. That doesn't really make a difference. The only thing that does make a difference with counting is how many nested loops we're going to have. There's a certain point where this starts becoming, it doesn't look great as far as, how the code looks, right? Nested loops are a little bit frowned down upon, but nested loops are how you do exhaustive counting. So, you can do this with nested loops, or you can do it with recursion. And I'm not going to argue that one of those is better than the other, except recursion looks a little cleaner. But, that said, this is nice and rudimentary. And it does allow you to start answering certain kinds of probabilistic questions. So, let's make another question here. And let's do something a little bit more complex. So choosing these 3 animals with replacement, what is the probability of getting at least 1 dog and no cat and no cats. So this is, essentially the same thing, and let's just mix this up a little bit. We're just going to edit this a little bit. The probability of getting at least one dog and no cats, at least one dog, no cats, and we just need to adjust this, this expression here on line 47. So we're going to count dogs, and we want this to be at least one, and we want to make sure animal arrangement of cat dot count. Oh, oops. Arrangement dot count of cat equals 0. Okay. So notice here we're just putting just a simple compound expression. You can do it like that. You could also nest this and say if that is equal to 0, those are going to be equivalent, although I'm missing something. There we go. And we're asking 2 questions, right? And we can make these compound by having them be ANDed. Either way is fine. Although it would be preferable to leave this on one line. But yeah, we can answer this question. And we can make these things more and more complex if we want to. Okay? I think that's important to recognize. So it looks like about a 0.26 probability that we're going to get at least one dog and no cats. We could print this out and look at it, but I feel like it is trustworthy. Okay, so let's think about other kinds of problems. Not using counting. We're going to cover counting in Premium Prep pretty soon, and as many of you probably know, we take our recordings from Premium Prep, and they're publicly available on YouTube. And definitely feel free to go watch those. There are recordings from prior Premium Preps where I go over counting, factorial permutations, combinations, and that's up there and available. And I think they're pretty clear. I'm mostly focusing in on how to think about iteration in this sense. Okay, so let's switch from counting to sampling. And I'm going to make a little bit of a justification for sampling. Oh, and at any point, if there's a learn problem you want to work on or anything like that, feel free to post it in the chat, and we can jump over to that after I get to a good wrap point for where we're at. Yeah, so let's talk about sampling, and I want to make kind of a justification for this. I draw a lot of these sort of, here's a circle, right? So let's say we have this massive set of possibilities, okay? And maybe an example that I'll use in class at some point is, 21 basketball players on a team. If we're going to make an exhaustive list of 5-player combinations, 5-player teams, that's going to be a little frustrating to do using this counting approach. That's going to be 5 nested loops. It's going to take a while to run, and maybe it's not it's not the only way to do this. It's not necessarily the best way to do it. There are times where problems become sort of intractable, and we might look at all the possibilities, but then decide that we're going to select, we're going to sample from all the possibilities instead, right? and we're going to build a representative sample and infer, or estimate, actually. We're going to estimate the probability of a certain outcome, given this much larger pool of data. So I'm going to try to just come up with a problem here. Maybe we'll stick in the animal realm. So let's say cat, dog, and fish, and let's say squirrel, beaver, tortoise. If you have any ideas for animals that you want to throw into the Slack, please feel free to do so. Eagle, shark. Anytime I think of the word eagle, I think of shark because of that Eagle versus Shark movie. Mongoose, nutria. Okay. So let's think of some rules. Let's think of just a few rules here. Let's say fish. Let's say we have one of each of these animals. Okay. We have one of each of these animals as pets. A fish cannot share a room, or the fish, I should say. Fish cannot share a room with the shark. The nutria cannot share a room with the squirrel. A tortoise cannot share a room with a dog or a cat for some reason. And eagle cannot share a room with a mongoose, a squirrel, or a beaver. I think that's enough rules. And I'm just gonna snag this whole thing. And put it up there. All right, so we've got all these animals, and we're trying to, what are we trying to do? We're trying to set up a room that has 4 animals in it, randomly selected. Let's do this. Construct possible, combinations of 4 animals that can occupy that room. So offhand, this isn't, this isn't a particularly easy problem to constrain into like a mathematical approach. Not offhand. And one of the things that we can do, and this isn't the only way, I want to be very clear about that, but we've got a phenomenon and we're trying to model it, and we want to be able to build this and then answer some questions. We want to use Python to explore answering this question. And this is really about, how do you do that? How do you start leveraging Python in a way that gets you to some kind of reasonable answer? So I'm going to utilize the choice function. So from random import choice, and we're going to build sets of 4 of these, right? So let's just write a function, def build set of 4, and why don't we pass in that list? So we'll pass in a list of items. I'm going to do this I'm going to do this simply, just very simple collector pattern. One thing to remember is that we can only have one of each item in a list, right? We only have one of each of these pets. So I'm going to do something like this. This is a good spot for a while loop, honestly, but I like setting these up as for loops. So for whatever in range, and I use an arbitrarily large number, so I don't think it's going to take us more than 50 tries here to construct this. I'm going to say output.choice, output.append a choice from our list. Okay, so at that point, maybe there's more I have to do. In fact, why don't I do this? Why don't I separate out this choice and say chosen. I'll just say whatever chosen animal this is. We're first going to check if it's in. If chosen is not in output, then we can append it, right? Easy. That's really straightforward. And after the append, we can ask a question. We can say if the length of output is greater than or equal to 4, we could just do equal then and be logically the same here. Then we can break the loop and we can return the output. So let's call this and see what we get. So build set of 4. And we get an error. I need to put in the animal list, right? Animals. That's what that is. No. It's called, no, it's called animals. Okay. Let's try that again. Append takes 1 argument, 0 were given. Well, let's fix that. Mongoose, cat, tortoise, fish. Dog, tortoise, nutria, cat. Fish, nutria, tortoise, mongoose. Shark, mongoose, fish, tortoise. Now, some of these, one thing we want to be careful of here is we're just putting these animals in a room. We don't care what order they're in when they're there. So I'm just going to do this. I'm going to say sorted. And this is going to make a standard order of these animals. So cat, dog, squirrel, tortoise, so they'll just always be in alphabetical order, and that's really what we want. Yeah. Okay, so that is building 4 animals, building these sets of 4 animals. Now, what we might want to do is build a data set of possibilities, right? I'm going to call this animals combinations. And again, so we're sampling here, right? We're sampling because we're taking choices from this set of animals that we have here. And now we're going to here, I'm sorry, let's let me paste this in for where we're at. If you have like an error there that you want to correct or anything like that. Now what we can do is, build some kind of list of animal combinations. And I'm going to do this in not the most efficient way. I just want to, give you fair warning of that. But I think it's helpful to approach this in a a simple approach. I think using a simple approach. There are better approaches, but I want to keep this pretty accessible. Okay, so if I'm going to populate animals combination, I'm going to do something. I'm going to call out to build set of 4 a certain number of times, okay? And we're going to pass in whatever this list is going to be, and I'll write this into a function. So def, what should we call this? Build animal comms, and we'll pass a list into that. I'll just call it build comms, why not? Because this should work for any list of elements. And we're going to do this a certain number of times, right? So for whatever in range, I don't know, let's do something arbitrarily large. Let's do 10,000. Let us get a set of 4, and then we need to check certain things, okay? We need to satisfy these rules above. So the fish cannot share a room with the shark. And I'm just going to do this with a stack of if statements, all right? So if set of 4 dot contains fish and set of 4 contains shark. Then we can continue. Continue here is just going to essentially throw this away. We don't need it at that point, so we can just throw it away. It's not a viable combination. And we can continue this. If the set of 4 contains nutria with a squirrel, those can't be in the same room. Then we can continue. Right, and kind of what you're seeing here is that this is just some simple logic. So a tortoise can't share a room with a dog or a cat. There's a couple ways that we could write this. So if tortoise is in there, and set of 4 contains cat, so that's one scenario. Or it contains a tortoise and contains a dog. Then that shouldn't work, right? And then an eagle cannot share a room with a mongoose, a squirrel, or a beaver. Okay. Let's think about how to do that. So again, there are multiple ways you could do this. So we're talking about an eagle, and it's like I want to write this as a comprehension and not this really long, drawn out conditional. But let's just do that this way. So mongoose, squirrel. Oh, whoops. That should stay eagle. No, that should be mongoose. And then or contains eagle, and set of 4 contains squirrel, or there's one more here. eagle and contains beaver. Okay, so we should have effectively satisfied these rules at this point. And you know, we haven't built anything yet, but let's go ahead and, you know, if this set of 4, whatever this set of 4 is, if it's not already in our animals combinations, and why don't I go ahead and put this in here. So if set of 4 is not in our animals combinations, then we can put it in there. So animals combinations dot append that set of 4. And we can go ahead and return our animals combinations, and we can take a look at what we get out of this. So why don't we just take a look and make sure that we are actually satisfying these rules, and you know, there's a chance that I made a logical error in there somewhere, and we should see about solving that. I don't know what that's. Okay, well, we'll find out. We'll see if there's any errors. List is not defined. Okay. This is going to be well, it's going to be animals, right? Yeah. Not there, but down there. Okay. Okay. Oh. There's no contains. That's from a different language. Let's change this to. We can do this like this. Eagle in set of 4. Oh. Sorry, y'all. This is what happens when you program in multiple languages. You think there's a contains method when there isn't. Eagle in set of 4. And let me start this over. Okay. All right, so eagle in set of 4 and mongoose in set of 4. Oh, I did this a lot. I will do my best to clean this up very quickly. to go? Alright, let's try that again. Okay, animals combination is not defined on line 112. Animals combinations. Okay. So, what we should be seeing here is a list of unique combinations. What do I mean by combinations? Well, it doesn't matter what order these are in. That's why I sorted them, if that makes sense, because sorting them prevents me from adding, two lists that have the same elements in them, and that allows me to build this. And notice it builds pretty quickly. We've got a lot of animals. This isn't taking that much time, but it is running 10,000 times. Now, here's a good question. Let's see how many animal combinations we are getting. And let's figure out if we're getting all of them. And we can do this through sort of observation. So 74, 74, 74, 74. I don't know. I think we're getting all of them. Now, if I increase this to, say, I don't know, 1 million, it'll take a little bit longer to run. But notice we're still getting 74. So if we were, according to these rules, if we were to ask the question, how many combinations of 4 animals can you have that occupy this room? Well, I think we answered that effectively using sampling. We don't have a closed formula for this according to these rules, but we have answered that question. And I think it's pretty cool, We can take this further in the same way that we took the last question, and I think 10,000 is probably enough iterations. I'll change that back so we don't have to wait. For all I know, 1,000 could be enough iterations, but let's just play it safe and do 10,000. Let's ask a question like, what is the probability of having a squirrel, a beaver, and a tortoise in the same room? Or maybe just a squirrel and a beaver. Let's do that. What is the probability of having a squirrel and beaver in the same room? So we can traverse this. We can traverse this animals combinations. And I'll just say for a combination in animal combinations, let's say if the combination, I was about to do dot contains again, but if squirrel in combination and beaver in combination, then let's collect that. Let's say, call this squirrel and beaver. Dot append combination. So if we want to just answer the probability, this is going to be, we can print the length of squirrel and beaver and divide that by the length of the animals combinations. If we want to see all of them, of course, we can traverse through, right? We could just do this. We can also just print squirrel and beaver in this for loop. Or print the combination in this for loop. Okay. So here are all the possibilities of having a squirrel and beaver in the same room. We can answer that question, right? We could easily pivot this a little bit. We could pivot this problem to be people's occupations, right? Let's say you have a set of employees and they each have specializations, and you want to build a team that satisfies certain specializations. You could determine that that team building through this algorithm. It's not necessarily the cleanest way to do it. There might be better ways to do it, but this does illustrate a kind of a way forward. Okay, we can answer some pretty complex probability questions as a result of this, right? We can figure out all the combinations that satisfy these rules. We can figure out subsets of those combinations, and I think this approach, this understanding, like playing around with this kind of problem is very beneficial. It's going to help you to think about how to approach solving problems. It doesn't have to be, you don't have to solve it in the best way. Sometimes it's just about solving it and getting to an answer. So I'll share that code and I'll comment some of this stuff out. Or, you know what, I can just delete all this. All right. So let's kind of, since we're in this space of counting and sampling, let's go back to numeric systems a little bit and get into the realm of binary. This is one of those things that we all associate with computers and blah, blah, blah. If you take, if you go into computer science, do a computer science degree or something like that, there is a lot of time spent on binary and a fair amount of time spent on hexadecimal, which is a base 16. Binary is base 2. There are only two possibilities, right? And we think of those possibilities as being 0 and 1 or false and true. Although that's a little bit arbitrary when you get down to it. So how do we count in binary? I'm going to count in 4-bit binary, so 4 bits. If there's 4 bits, that means that it's 1, 2, 3, 4 bits. Each one of these is a bit. Each place is a bit. So a bit is either 1 or 0, and what we call this is a 4-bit binary word. But a lot of people just say 4-bit binary number. That's fine as well. So if we're counting in this, that's 1, right? So we've got 0, then 1, and 0, 0. This is interesting because we only have 2 components of this. We only have 2 elements. Oops. We only have 2 elements of, to count with, 2 numbers. So once we get to 1, we flip this 1 over back to 0 and increment the next one. So we get 0, 0, 1, 0. Then the next one is going to be 0, 0, 1, 1. And then we flip that over, and we're going to get 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. Okay. So that's something that we can count. We can count through these. And it's easy enough to count through these. Let's just do that with Python really fast. So here's some counting, and let's put a description here saying count all possibilities in 4-bit binary. Okay, so we're using 0 and 1. These are our bits. And we can say for bit in bits, and we'll do bit 1, bit 2, bit 3, bit 4. Okay. And we're going to, we'll call this 4-bit binary, and we will pack this list in with binary. All right, so we're going to append a list that contains bit 1, bit 2, bit 3, and bit 4. And so print this. Actually, let's do a for loop and just iterate through this and print each. So for each word in 4-bit binary, let's go ahead and print the word. Okay, so that's what we're seeing, and that's exactly the same thing that we just wrote out. So I think that's nice. That's fairly simple. Notice that's that same pattern. You know, we get to 1 and then we roll over back to 0 and we increment the next one. Base 2, you know, binary is just as simple as base 10 or base 16 or base 73. You know, they're all the same idea. So let's think about relationship between binary and decimal. I think that's sometimes a nice thing to think about. 0 we can represent as 0, 0, 0, 0. Now, on a computer level, you know, on a hardware level, we're not necessarily going to do that. That's not exactly true. But for our purposes, in sort of an abstract number representation, this is true enough, right? This is true. So 0 we represent as all zeros. 1, 0, 0, 0, 1. 2, well, we're going to just roll over this 1, is 0, 0, 1, 0. 3 is 0, 0, 1, 1. And let's go to 15, which is going to be 1, 1, 1, 1. 14, which is going to be 1, 1, 1, 0. 1, 1, 0, 1 for 13. And let's just think about these, let's break these out. So we could count through these, right? We could use nested for loops and count through these, and we're going to see this kind of, you know, 0, 1, 2, 3, you know, 4, 5, 6, 7, 8, 9, 10, up to 15. If we enumerate, or if we, you know, have a counter that we're just outputting alongside this. But we might think about this a little bit differently. We can think about this in terms of place value. And what do I mean by that? Well, let's think about the number 999. This is what we call the ones place, right? This is the tens place. This is the hundreds place. And if we wanted to calculate this, to really translate it out, we could say this is 9 times 1 plus 9 times 10 plus 9 times 100. And I think that's, you know, that's pretty understandable. Like, that's pretty straightforward when we think about it in decimal. Now, what about this number? Let's do number 13, so 1101. This is the ones place. Still, you know, it's the ones place. It's binary, it's base 2. This is the twos place. This is the fours place. This is the eights place. So this is 1 times 1 plus 0 times 2 plus 4 times 1 plus 8 times 1. So this is 8 plus 4 plus 0, right? Plus 1. 8 plus 4 is 12, plus 1 is 13. So we can see that. We can see how that might work. Now, let's look at this in a couple ways. The first way is simply, well, let's build a dictionary. And let's do this. So let's make this a dictionary instead. And let's say, let's just say we have a counter. I think that's an easy way to start. We'll start our counter at 0. And here we're going to say 4-bit binary sub counter is going to get this list. And then we can increment the counter. Okay. So we can't traverse this in quite the same way. Let's look at it first, as a dictionary. I think that can be helpful. So let's print that dictionary. It's a little hard to read in this format, but if we traverse this dictionary like so, let's do for binary in 4-bit binary items. Items is going to essentially, so for decimal and binary in 4-bit binary. That dot items is going to get us out a tuple, which we then unpack into decimal and binary. And then we can print the decimal alongside the binary. Okay. So let's see what that looks like. And that's nice. 0 is all zeros, 13 is 1101. Nothing too surprising there. We could extrapolate this out for, a larger number if we wanted. So I'm going to paste this in, and then I'm going to kind of maybe turn this on its head a little bit. Notice that this requires iteration. It requires that we really go through. If we wanted to count up to 370, we would have to have enough nested loops to do that, and that may not be what we want to do. And I think we could approach a better algorithm for this. And so there's an algorithm called decimal to binary, or dec to bin is what it's often called. And I'm going to go ahead and, why don't we sort of walk through this algorithm. And I think this is one of those things that's like, you don't necessarily need to know how to do this offhand. But if you're given an algorithm, it's nice to be able to implement it in Python. So I'm going to go ahead and I'll just delete all of this for the moment. So let me write out this algorithm. This is dec. We often do this. Dec to bin, where bin just means binary. And this is, let's say we have a decimal number. Given a decimal number, we're going to take the modulus by 2. Right? And if you think about it, modulus by 2 is either going to give us a 0 or a 1. Huh? So we can set aside that result. So we set aside the result, and we then floor divide, right? That's our backslashes, double backslashes by 2. So we're dividing without remainder. And we do this, so we should probably put a, do this while our number is greater than 0. And then once we finish all that, we need to reverse the order of the bits. Okay. So that may be a little confusing, but let's walk through that, and we'll kind of just write this as code, and think about this as one of those kind of beginner algorithms that are pretty cool. But you know what? Let me actually walk through a problem where I'm doing this. So let's take the number 27, and we're gonna do dec to bin on this. So 27 mod 2 is going to be 1. 27 floor divide by 2 is going to be 13. Right? So, sorry, I had to prove that to myself in my head for a second. 13 mod 2 is going to be 1. And 13 floor divide 2 is going to be 6. 6 mod 2 is going to be 0. 6 floor divide 2 is going to be 3. 3 mod 2 is going to be 1. And 3 floor divide 2 is going to be 1. And then 1 mod 2. Well, what is 1 mod 2? Think about that. If we perform 1 mod 2, and then this is how we can just prove these things to ourselves. That's 1. Okay. 1 mod 2 is 1. 1 floor divide 2 is 0. Well, what is 0 mod 2? Let's find out. It's just 0 mod 2. Well, that's 0. And then what is 0 floor divide 2? Well, that's 0. Then 0 mod 2 is 0, and so on. So we've finished our operation here. Okay? Now, to finish out this algorithm, we're going to take this from the last value up to the first. So 27, unless I made some kind of mistake here, should be equivalent to 11011. Well, let's prove this to ourselves and write this algorithm out in Python. And I'm going to call this dec to bin. So this will just be a function, dec to bin. And we're going to pass in a decimal number that we're going to convert. Now, I'm going to set a number of bits. I like doing this because there's this idea that, maybe isn't obvious. There are these kind of, common lengths of binary words. 5 is not a common length, So if we were to represent 27, we would probably represent it in 8-bit binary, where it'd be 000 11011. So I kind of want to, pad in, we call this padding zeros. I might want to pad in 3 zeros. So that is what I'm going to do. So number of bits is 8 by default, and I'm just going to collect this binary into a list. So the first thing I'm going to do, I don't want to modify this decimal number directly. I'm going to actually modify it. I'm going to modify a copy of it. So I'm just making another value that I'm calling x. So I'm going to do, for the number of bits, I'm going to perform this operation. I'm going to do this operation as many times as there are bits. So for whatever in range, and I'll do the number of bits. Each bit, the bit is going to be that number mod 2. And then I can just collect that. I'm going to collect bit into a binary list. And then I need to floor divide, right? Floor divide by 2. That's it. So we don't want to just return the bin list. We want to return the reversed version of that bin list. And the way that I do that generally is : -1. That means we're going to start at the end and go all the way to the beginning. The other way you could do this would be reversed of the bin list. However, you do need to cast this back to a list. So list of reversed of bin list. That would work as well. I'm not as much in favor of that. I like this form a little bit more. Oops. Okay, so let's do dec to bin of what did we do? 27, and see if this works. And also, see if I did that by hand correctly. So we'll run tell.py. So 11011, is that what we found out? Yeah, 11011. So this algorithm looks like it's working. And let's expand on this just a little bit. And something I want to point out is, I want to point out a couple things. This algorithm here, why don't I just do this? Let's put in 984. Okay. And if you want to know how many bits it would take to represent that, one thing we can do, if we want to know the largest number we can represent with 8 bits in this form, that is just 2 to the 8. Okay, so we can represent up to 256. What can we represent? Can we represent 984? Not exactly. We can represent something like 984. So we can represent this. We can represent 984. But if you think about modulo, it's sort of circular. So at some point we got back to 0, and then we got back to 0 again, and then we got back to 0 again, and ultimately we ended up with 984. Now, that's, if we want to satisfy 984, we're going to have to add more bits, and we should be able to easily do that with 12. Right? So what is 2 to the 12? Oops. 4096. Let's go ahead and run that again. So that's a good representation of 984. And something I want to point out to you is this binary pattern, 110110000, exists within this other binary pattern, 110110000. So I think of that as being circular. Modulo as being, the modulus as being a circular operation. But, we don't have to dig into that really here. So one last thing I want to do here, and I'll paste this function in. One last thing I want to do here is pack values into a dictionary. Okay. So I'm going to create a dictionary. just going to call it D. And I want to count in this dictionary up to a certain number of values. What do I want to do up to? Let's do up to 512. And there's something. Actually, let's do to 256. And there's something I want to, point out. So I'm going to do something a little bit wrong here. For decimal in range, and we're going to go up to 256 and include 256. Okay. We're going to say D sub. Oh my gosh, pop-ups. D sub decimal is going to be dec to bin of dec and num bits of 8. Okay, so for decimal and binary in d.items, let's print the dec and let's print the binary. So this is kind of nice. This isn't a nested for loop approach, right? There's something a little bit nicer than this, but also consider that in some sense it is a nested for loop approach. We just aren't showing nested fors. There is a for loop here, and there is, so there is a single for loop, but we're not nesting a whole bunch of for loops. So this is a little bit more straightforward. It's a little bit better than what we did before. If we wanted to do 8 nested for loops, we could do that and we could construct this, but using this algorithm, this dec to bin algorithm, this is a little nicer. So here we are counting up to 256. Notice 256 is all zeros because the largest number that we can represent in 8-bit binary is 255, because all zeros is representative of 0. That's not to say that 256 is not also this, but to effectively distinguish this from 256 from 0, we would need another bit right here. So if you're coming from a CSS background, or if you've messed with images, or extensively with images at all, you probably realize that 0 to 255 is luminance in images, in one of the representations for luminance, right? The R pixel can be 0 to 255. If it's 255 and the other 2 pixels are zeros, then that's red. If green is 255 and red and blue are zeros, then it's blue, and so on. So 8 bits are often used to encode color. That's just something that's out in the world. That's something you can dig into a little bit later. So that's study hall. Actually, let me paste this in. It's easy enough. So that's study hall for today. In study halls, always feel free to ask questions. Always, if you have something on Learn that you're stuck on, definitely bring it up. Whoever's hosting that's a primary purpose of study halls, and otherwise we go over, stuff like this. We explore data structures and lists, and data structures and algorithms, simple algorithms. We might dig into something that's a little more complex or over some people's heads from time to time, but ultimately what we're trying to do here is provide a place to gain a little bit more knowledge, a little more skill, code along, but definitely a place to ask questions. So thanks so much for being here, and for those of you in Premium Prep, I will see you believe I'll see you on Tuesday. And for everyone else, always reach out. And, you know, if there's some place where you're significantly stuck and you need some help forward, you know, post in the channel, of course, and we'll either answer that way, or if it's something where you still don't understand after posting, reach out to us directly, either to me or to anyone on our team. Cool. Thanks so much. I'm Tovio.